ठीक है, so I guess more of you are not coming. You can come in front, huh? Come in front. इधर आ जाओ ना, 2 रोज खाली है. Recording start. Alright, so what we'll do is, I think the others will probably listen to the recording then. So we'll talk about types of random variable. I'll briefly talk about countability, so that you are, aware of what's going on. So to define countable set, we need to define what is the cardinality of a set. And to define the cardinality, we need to define their mapping, one-to-one onto mapping. So we first write the two definitions. F going from A to B is one-to-one if for A1 not equal to A2 in A, f of A1 is not equal to f of A2 in B. So this is definition of one-to-one. Is this one-to-one? Guys, why? Because A1 and A2 are distinct, but F1, FA1 and FA2 are same. Is this possible that you go from one this to this? It's not even a function. Everybody understands? And can you have that you have a point and not have a mapping? That also is not possible, because it's the domain. The function is defined on the domain, right? So this is a function, this is the domain of the function. So that's one-to-one. Now what is onto? F going from A to B is onto if given B belonging to B, there exists at least one A belonging to A such that f of A is equal to B. Which means that a case where you have every point mapped but you have an extra point here is not possible. That is what it's saying, that if there is a point here, it should have a reverse mapping back here. Is that okay? So that's one-to-one. Example, if A is 0 to 1 and B is 0 to 2, and you've got fx is equal to x. So is this one-to-one or onto or both? Sorry? It is one-to-one? Onto? No? Why? You draw it, the best way is to draw 0, 1, 2, 0, 1, this is the function. So of course for every value, distinct value of this, there is a value of B, but there are values of B for which there is no mapping of A. So this is one-to-one, not onto. Another example, A is minus 1, 1, B is 0, 1, and fx is equal to x squared. What is this? It's onto but not one-to-one. Why? Best to draw it. This is f of x square, y is equal to x square, and this is minus 1, this is 1. So every value of the domain is mapped to a value of B, but there are two values here. So that's why it's not one-to-one but onto. Every value of B is mapped, so that's why it's onto, but it's not one-to-one. That these are different, but they're giving the same B value. Okay, so now that brings us to the countability and the cardinality. So there is the definition. Two sets A comma B have the same cardinality if there exists A belonging to B that is one-to-one and onto. So the two sets have same cardinality, and what is countable? An infinite set is countable if it has the same cardinality to set of natural numbers. Okay, so cardinality is if there is between two sets have the same cardinality, you can find a mapping one-to-one and onto, and it is countable if it has the same cardinality as the set of natural numbers. This is what you have been taught in the discrete mathematics or something else? Same thing? Okay. So just a revision. We'll now move to, before I write the few examples. So this set, is it countable? Sometimes we have to prove it actually, so it's not that obvious. Z, Q, 0, 1. Is this countable? You can prove that there is a one-to-one mapping to natural numbers. This is a set of even numbers. You can always find one-to-one mapping with onto mapping. The set of integers also are countable. You can prove all of this, by the way, which I am not doing. I assume you did it. The set of rational numbers, which is m over n, where m comma n belong to the set of integers and n is not equal to 0. So this is also countable, while a set of real numbers is not countable, and you can prove it in our advanced calculus class. This is the proof of this is actually done. Okay. Everybody okay? This was a primer of what you did in discrete mathematics. Now we start with the discrete random variable. Okay, so what does the definition of the discrete random variable say? That which I already told in the class before. A discrete random variable is one in which may take only a countable number of distinct values. So if a random number takes random variable, sorry, I shouldn't say number, random variable takes finite values, then finite distinct values means they are different from each other, or write it more specifically, finite number of distinct then it must be discrete. This is what I told in the first lecture, that if the range of the random variable is finite or it is countably infinite. So is the set of rational number, can there be a discrete random variable? Yes or no? How many say yes? How many say no? It's a countable set, so it is that, you know, real numbers are not. Okay. So from axiom, sorry. Okay. So examples are anything, you know, number of children, number of, where you're counting something, that is all discrete random variables. So I'll not write the example. So we'll write the definition, another definition. Suppose a random variable x may take k different values with probability that capital equal to xi is defined to be the examples of discrete random variables I've just written include number of children in a family, the Friday night attendance at cinema, number of patients, number of defective light bulbs. So anywhere there is a number, it's a discrete random variable because it's discrete and it's finite. Defined to be Pi is equal to P of x is equal to xi. So this value at a particular point of the random variable is called the probability mass function. And the idea of the mass function, which was not obvious in books, came out that there is a weight or a concentration. So these values are getting masked at different places. So I'll talk about this when I talk about density again at the end, why it's called mass, why the other one is called density. So that's going to come back again. There is a notational, although we are using it this way, this is a small p by the way. Sometimes, and this is a capital P, sometimes people want to write it like this probability mass function, or sometimes they also want to write it like this. So it depends what the notation you're following. You want to carry the random number with you, you want to carry the full variable where you're computing the probability mass function, or you just write Pi for the change in the values of the discrete random variable. Is that okay? Okay, so we say this is called the probability mass function or PMF. We already said why it is called a mass, which we are going to do again. Okay, from axioms, or the third axiom, what do we know? That the sum of the probabilities is 0. So P1 plus P2 plus Pk is equal to 1, or so because we are saying the random variable is taking k different values, so that's why I've added till k. Or k can tend to infinity, which means that you can always write it I is equal to 1 to infinity is equal to 1. Why? Because these are mapping whole of these events are mapping all of your sample space, and this is probability of each of them, P1, P2, P3, Pk. So the total probability of the sample space is 1. So the sum of the discrete individual probability is always 1. Right? Everybody comfortable? So example 1. Well, he has drawn it. I don't want to draw the whole picture, but I'll still write it. This is the case of probability mass function of sum of two dice. What will be that? So 2 over 6. This is 6 over 36. And this is 5 over 36. So if you draw it, let's say this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you draw all of them, so the probability mass function for this we have seen already when we were defining the random variable itself was 1 over 36, right? Because the sum 2 would be only in the case when it's 1 comma 1, and the sum 12 would also only be in the case when it is 6 comma 6, and the case of 7 was the longest. In this case they had 6 combination. You had 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. 6 of them were there, so it's 6 over 36. So you can see it kind of forms a bell graph, but not in a discrete sense. So this is 5 over 36, and then it goes down both directions. But probability mass function is individual values at a point. It's never a curve, right? So just don't get confused. I'm just telling you how it looks like. Okay, I'm going a little fast because this is fairly straightforward. So the question goes that again you have let x be sum of two fair dice. Two fair dice rolls. Now suppose we are interested in probability such that x is in the interval 1 comma 4. I've not written the whole question, but I've written it down. Let x be the sum of two fair dice rolls. That's a random variable. Now suppose you are interested in probability such that x is in the interval 1 comma 4. So what probability are you interested? 1 is less than x is less than 4. Everybody with me? What values can x take in this one? Sorry? 2. Yes. So 1 will not be there, right? You're rolling 2 dices. So it will be only 2, 3 and 4. So although there is a range, but x can be 2 or x can be 3 or x can be 4. Yes? Now what do we do? Now you'll just not forget the axiom number 3. These are f of p of x equal to 2, x equal to 3, x equal to 4 because they are mutually exclusive. We just add them up. So this is probability of x is equal to 2 plus probability of x is equal to 3 plus probability of x is equal to 4. Which is, what is this? 1 by 36. This is 2 by 36. 3 by 36, so it's 1 by 6. These PMFs we have already computed earlier. Sure. Yes or no? Everybody comfortable? So we'll just move on to the next. You'll do, when we do the tutorial, now the tutorial will happen on Monday on random variables, distribution, discrete and continuous. So there we'll have more harder problems to come along, because I'm telling you for the first time, so I'm not going into too much hard examples. And then we'll put set of 10 practice problem for whole of probability. So that will also carry more harder problems. But just make sure that if you go back home and read the lectures or listen to it, that these terminologies you don't confuse. That should be the idea, that if you are clear with the terminologies. Okay, so we start with continuous random variable. Okay, so you know it, continuous random, the range is infinite, where it's a continuum of range. So I'll just write it down. A continuous random variable, I'm not writing it, you don't abbreviate it to CRV, but I'm just writing is one which takes an infinite number of possible values. And when we say infinite, we usually mean uncountable. So there is a definition which follows this. Are usually measurements and examples which a lot of sources say is you're computing height, weight, amount of sugar in the orange juice, or the time required to run a mile. So any measurement which you are doing will be a continuous random variable. Okay. So we'll now write a formal definition of this, which kind of combines. In the discrete case, I wrote the definition which was just saying that the range is countable distinct values, right? And then I wrote the definition of probability mass function, which is just the probability of the random variable at a particular point is defined as the probability mass function, massing of the probability at certain points. That is how it is called. Here we are defining it differently. This is not the definition, this is intuition. The continuous random variable involves the probability density function. Like in the definition of the discrete random variable, we didn't use the definition of probability mass function. But here in the definition of the continuous random variable, we have to use PDF. So we'll see what it says. So we say that X is a continuous random variable if there exists a non-negative function f of x defined for all real minus infinity to infinity, having the property that for any set B of real numbers probability of x belonging to B is given by B f of x d of x. The function f of x called the probability density function. So let's read it. So this is kind of combining the definition of the continuous random variable and the definition of the probability density function. Although in the discrete case we wrote the definition of the discrete random variable and the probability mass function separately. Here we are combining the two. So we say that x is a continuous random variable if there exists a non-negative function defined for all x. So your first thing is there should be some non-negative function which is defined on minus infinity and having the property that for any set of real numbers b, so this set of real numbers b is coming from the fact that x is belonging to all the real numbers and you're picking a set from that. So from all of the available x values, you're picking a b set and the probability of that is the integral of that. If you can show this, then it is a continuous random variable and this guy is called the probability density function. The end of the lecture I'll tell you why this is called density, but intuitively if you try to look at it, what is density? Density is mass divided by volume. Everybody agrees? Let's say I'm working in one dimension, not in three dimension. So then the volume would be what? Just the length. Correct? So you can say that the mass is density times the length intuitively. And when you are doing this like component wise, which I'll tell you, so this product, the density into the length is actually giving you some sort of a massing of the probability. And that is why massing, again a concentration of probability but in a spread out way because it's all continuous. So hence the name density. I'll tell it more formally at the end. I'll write it down, which is in my notes. But that's the idea, okay? Okay, so from the axiom, what do we know? That 1 is equal to the probability x belonging to what? Minus infinity to infinity, right? If this is I'm calling the range of my random variable, then this is what it is. Small x is capital X. So this is equal to minus infinity to infinity f of x dx by just this definition. So ideally it's saying the integral of the probability density function over all of the space is 1. That is what we are saying. Like we were saying in the case of discrete, the summation of all the probability mass functions over the space was equal to 1. Here we are saying integral of that is again giving the probability sum, or sum of infinitely small elements is equal to 1. Okay, so that's the analogy. So there is a note. There are two notes. The first note is, what if b is equal to a comma b? Let's say the domain is not minus infinity to infinity. Then the probability of a belonging to x to b will be integral a to b fx dx. The second note is, what if b is just a point? Then what happens to the probability? If it's a point, the range is a point in case of a continuous random variable, then the probability becomes integral from a to a fx dx, which is 0. So for a continuous random variable, the probability at any point is actually 0 because you're looking at a range. That makes sense, guys? I'm confusing you. Okay? Alright. So it says the probability that a continuous random variable assume any particular value is 0. So example, see what time it is. So we have time. So the example, suppose x is a continuous random variable with PDF. So PDF and PMF are completely two different things. They are not analogous to each other. You should understand that. Because PDF is referring to the density, it's multiplied with the distance and then it gives the mass or the probability. Well, the probability mass function is actually the probability. Is that clear? That little variation, just keep it in mind. So it's given the PDF of this is f of x is equal to c times 4x minus 2x square with 0 is less than x is less than 2 and it is 0 otherwise. So there are two questions which they are asking. So the first question says, what is the value of C? And the B thing is saying find probability for x greater than 1. So one thing you notice that it's not giving you what the values x contains. It says the continuous random with PDF is this, and the PDF has a range. What's the range of the PDF? What's the range of the PDF? It's the whole of the real line, right? Because it's saying from 0 to 2 is something, otherwise it's minus infinity. So the range of the random continuous random variable can take any value. Can you do it? Tell me what C we are getting. Huh? No, you've done it already. Those who have not done it, can you do it, please? I forgot your name. अच्छा देखो प्लीज तो हंसी भी आए इनको. Anybody besides Manan who has done it? Do it, no? Done it? How will you do it? Attempt it, na? Alright, so still write it down for those who have not written it down. Girls, you making progress? Should I write the solution? Yes or no? I don't want to lose people in the class. The idea would be so that integral will be equal to 1. Why? Because over all of the space the integral is 1 and the space is only defined by this. So that was the only trick. Okay, so I'll write it down. So what do we know? Minus infinity to infinity, because that's the range of my random variable is 1. This is 0, only it's valid in 0 to 2. So this would imply that between 0 to 2, C of 4x minus 2x square dx is equal to 1. Yes, girls? Here, which implies that C of 2x square minus 2 over 3x cube, putting from 0 to 2, is equal equal to 1, turns out C is equal to 3 over 8. How would we do Px greater than 1? Right. So you'll take it from 1 to positive infinity of fx dx. Again, it's 0, so you'll do 1 to 2. You already know C is 3 over 8. So this is 4x square minus 4x minus 2x square dx. And you integrate this and you get a value of half. So in one sense, the continuous random variables are more closer to what you have seen, because it simplifies to an integral, and you've already worked in calculus with a lot of continuous things. The discrete ones are a little more difficult to get a handle on because that's new to you, but with the discrete mathematics going parallelly with you, I think you'll get more and more comfortable. Everybody okay this side? So what I'll do, last thing is I'll just motivate the probability mass and probability density formally once. This doesn't talk in the book, but it was in the MIT lecture notes which Kuldeep actually helped me found, and I found this explanation to be nice. So I thought I'll just go over it. So the question is probability mass and probability density. So we define it better. So let's say we have a rod of points. We've got x1, x2, x3, x4, and we've got some mass values here, m1, m2, m3, m4. So we define a mass function which maps these values p of x, small p of x, such that p of xj is equal to mj, but j is equal to 1 to 4 and 0 otherwise. So the total mass here is nothing but px1 plus px2 px4. So the probability is exactly the same, except that you replace the mass with the probability of the random variable at that particular point. So this is more straightforward. Density explanation is a little more better. So in the density explanation, it says suppose you have a rod 0, x1, x2, x3 till xi, and stopping at xn is equal to L. Okay. And then we make these segments about it. So the question is, or given is, suppose a rod of length L meters with varying density Fx, which is given by kg per meter. So at this xi point, so the mass of this ith piece, we have broken this into different pieces, the first, second, third, fourth, and so on and so forth. Mass of ith piece would be what? Fxi div times, let's say the interval each of these is delta x. So it will be that small, very small interval which you have distributed into times this. So if you have to find the total mass, which would be summation of I going to whatever 1 to infinity or 1 to n because they are n elements, fxi times delta x. Then you would write this in the integral form going from 0 to L fx dx. If you make delta x tending to 0, then it becomes an integral. So now this is the mass, which is, you know, density times the length. So instead of the mass, we are working with probability. So that is how you see. Everybody okay? All right, so we'll just stop here. I know you need more interesting questions in this, but just go over it once so that you are better off with the terminologies at least. Hai? Don't get confused in the terminologies. More harder problems we'll do in the tutorial and the practice problems. He sent a joke, so let's just see. You are already so tired. I'm sorry for taking your whole day because I think from 9:30 till now you're still taking classes or lab. But the good part is that tomorrow you'll be almost so free. You already have so many free periods. Wednesday second half is free for you. So in that sense, you'll relax and sleep. So this is in Hindi, but I'll have to translate. So a dentist said to Monu, I would need to take out your tooth because it has gone bad. Then Monu says, how much money will it take? The doctor says only 500 rupees. Then Monu says, can you take 50 rupees and make it a little loose? I'll take it out by myself. Thank you. So see you next Monday.